Hello, everybody, and thanks for joining another week of Water Talks here. Again, we're happy to have Javi back presenting, kind of giving a preview of the presentation he was accepted at later to give at what conference was it again, Javi?
Smart water utilities.
Smart Water
Also a couple
Utilities.
over on the East Coast, but yeah,
Perfect, perfect. All right, thank you all for joining us here. Next slide here, Javi.
yeah, of course.
All right, so just a little bit about us for those of you who are new to Water Talks. My name is Tim Adiris. I am a solutions engineer here at Innovyze. I've been with Innovyze for 5 years now out of Colorado, focused mainly on our asset management solutions. And I am happy to have a better connection than last week when I had to drop off from up in the mountains of Leadville, Colorado. So I'll be able to hopefully help Javi out with the questions. But for the most part, yeah, Javi, this is your show. Do you want to introduce yourself here?
Yeah, so my name's Javier Cantu. I'm the digital solutions architect. I work with customers in defining which ones of our solutions, whether they'd be on hydraulics or AI, ML, or anything like that, they need to solve their specific problems. It all fits in with our platform approach, all the stuff that I'm going to be talking about here shortly.
Perfect. Thanks, Javi. Again, for those of you who might be new to Water Talks, the goal here is to really focus on your questions. Javi, this is great for Javi to have his presentation. For more folks than those folks just going to the conference in a month here or so, please do type in your questions. We will try to put an emphasis on getting to those. And if we don't get to them, rest assured we will try to answer them after the 1 hour talk here today. Just a little bit on upcoming events and upcoming Water Talks topics. Not all these are on our website. I just finalized some of these topics just yesterday here. So, but this hopefully will give you an idea of what we're looking at next week, focusing really on day in the life of the actual day-to-day effects of having live stormwater modeling within a utility. So we've maybe you haven't heard us talk about some of our live modeling solutions. Sometimes it's hard to figure out, okay, exactly how will that affect my job? That's what next week's Water Talk is about next week. After that, we'll be taking a week off for Labor Day. On September 14th, we're still focused on kind of sanitary storm flood modeling. A couple weeks, month ago, we did a talk about hydraulic modeling calibration on the water distribution side. This is kind of that same talk on the collection network side. So sanitary storm flood model, looking at how to actually calibrate and keep that model up to date, which is always a struggle, we know, with all of our customers and utilities and consultants out there. And then,
ICM, right?
yeah, that'll focus a bit on ICM, but it's still relevant to all our different storm sewer and flood products if you're using InfoSwim or an InfoSewer and XP product as well. On September 21st and then 28th too, we're happy to bring back a couple guest speakers. I guess not bring back, but have our guest speaker from outside Innovyze for the first time in a while. On the 21st, it'll mostly be focused on asset management. So we'll have a consultant coming on for that, talking about how they used InfoAsset for a California utility. And then on the 28th, we're looking to have DeKalb County on, talking about their modeling experience and getting into the weeds and technical analysis with InfoWorks ICM. And then beyond that, what we're really looking at in October, and please sound off in the questions or in the survey at the end, kind of what are your thoughts and questions and interest around the infrastructure bill that's going through Congress is still held up now, but it's close, right? Around that bill and
So
water.
close.
It's so close. I was just reading
Yeah.
this. It's been held up by a senator I'd never heard of before. But anyways, that's going to be a huge impact on water. We will be talking about it for sure once it's official, and kind of looking at how can we prepare utilities for the monies that are going to be allocated in that. How do our solutions kind of intersect with things that are in that bill? But we want to hear from you so that we can target some of those topics to what you all are interested in once that bill is official as well. So please do sound off in the questions or in the survey at the end there. All right,
Yeah,
with
no,
that,
I'm excited for that. I would definitely say if you have particular questions about how some of those monies will be appropriated or something like that, I would love to incorporate that into agendas and other water talks, Just really depends what you guys want to know. But there's a lot there that's going to affect the industry, and not just the actual stuff that's shovel ready, but also the digitization of the industry that we'd love to speak more about. Yeah.
Hmm. Yeah, I got some good stuff in there. We've had some folks that I think have maybe read more of that than a couple of congressmen, maybe not. We'll see, but we're reading through it ourselves for sure. Um, Anyways, with that, I'll hand it over to you, Javi. Um, yeah, thanks for joining us
No?
again today.
Yeah, no, I appreciate it. Well, guys, today I'm going to talk about AI-enabled utilities across the entire water cycle. I do want to go through a couple of use cases, pretty much everywhere, uh, whether it be in distribution, collection, treatment, discharge, wherever it may be. Um, I am practicing for a couple of presentations I have coming up, but I welcome interruptions. I welcome questions. Timothy is here to interrupt me where needed. That being said, I'm just going to jump right into it, and please stop me wherever you guys want to talk more details on. Um, so why AI? I may have presented this in the past, but I am going to skim real fast through just the very beginning here. Um, Anywhere within our industry, we are making very complex decisions every single day when it comes to operating our systems. And a lot of those decisions are based off our judgment and experience. There's way too much going on right now that just craves the attention of technology, and it craves more solutions in technology. Um, a little bit about AI and ML. I think the simplest way I can describe this without going into way too many details of data analytics and data science is to think of ML as Marie Kondo of your data, right? It is your organizer, it is your tidy upper, like machine learning is a labeler. And that is what we need nowadays, right? Whether it's in change management, staff turnover, wherever you may be, something that is automated in the background, taking the data, labeling, saying, hey, this belongs here, this is what it means, and this is when it should be used. That's what machine learning does at the end of the day. And who wouldn't want that kind of joy sparked in their life? Very horrible pun there, but you know what? I'll probably take that out of um my script later. A little bit of what I'm saying, what I'm going to be talking about is also the approach that machine learning takes to solve a lot of water problems, right? Machine learning and AI as a whole lands more on the operational performance management strategy. This is a strategy, not a software. It's not a thing. It's a strategy to solve problems. A lot of the things, and a lot of our core solutions, when you look at IAP, Info Asset Planner, maybe even our hydraulic models or something in between, they land more on the asset performance management kind of strategy or just advanced performance management when you look at numerical models or anything like that. Either way, I like to separate that as APM kind of strategy where you look at a very specific component of your system to figure out how it may be affecting your overall system. But the OPM approach, that operations performance management approach, really relies on an outcome-based approach. What are you trying to do, and what gaps do you need to fill in order to make that happen, right? As everyone knows now, we've done a lot of targeting out there now, and a lot of marketing around our platform, our Info360 platform. A lot of our solutions are being slowly rolled up into what is Info360, that one platform available. This is going to allow us to use that OPM management or that OPM approach to start solving some more complex data sets as the ones that I'm going to go over here shortly. Little debrief about how a majority of our treatment models or even distribution model works is talk about how we optimize using machine learning. So when we optimize using machine learning, and this example here is for treatment, but I will talk about how it works also in distribution here shortly. Um, the way it works is we look at this data set and we use this entire data set to start fingerprinting and abstract a process uh, to predict a production or a feed quality, an input, whatever that may be. Maybe you have a water quality input that needs to be predicted. Sometimes there's a demand that needs to be predicted to a season, to a time of day, to a very specific event happening. I know with a couple of clients, we find that, whenever there's a hockey game, we see a huge demand spike on the water demand profile, and we can predict that based off these set schedules on social media or anything like that. So the first step of the process is training models to predict good demand models or generate good demand models or water quality models. From there, we can recommend control actions for pumps, distributions, the recycle rates, blowers, compressors, even something such as odor control within a system based on what's required on specific inputs. We do this by looking at historical data and saying, okay, well, what resulted in what specific set points resulted on a very particular product stream, whether that be an output in a discharge or drinking water. Based off very specific rules, such as compliance limits or specific operational targets like cost targets, uh, we have several iterations work, sometimes in tiered statistical analysis or sometimes numerical models, such as our hydraulic calculations, create thousands of iterations to determine, okay, what different types of approaches can we take to result in a very specific product stream to meet the predicted demand. Based on those iterations, we can output very specific output control actions for a system. We can do it on a 24-hour scale. We can do it on the 1-hour scale. We can react to something that's going to happen in 4 hours, right? Really depends on what you're looking to predict and how far you're forecasting your data out. So getting right into some of the places where all this technology is applicable. And then I'd like to stop here after each and every single one of these and see where we can possibly get more questions answered. So Tim, you'll have to interrupt me
Yeah.
right after I finish here on the water treatment, which is kind of where I'm going to start, right?
Okay. You don't want to do a question first here?
Oh yeah, if there's a question,
Yeah, yeah.
definitely.
I'm popping on because there's a question. From David, before you get into kind of the use cases, what threats and issues does using AI present for cybersecurity?
Well, that's a very good question. It really depends, but network architecture is really going to be like the prevailing science behind determining the threats that AI brings to this, right? At the end of the day, AI can only do what you tell it to do. It's not going to go beyond bounds or limits because the models are constrained by something like compliance limits. It's not going to, let's say, overdose on a chemical if you already have a max chemical require or you have a max chemical limit that will ever give, right? So in that kind of regard, there AI isn't the threat. In data security, there's always that threat, right? There's no system that's perfect. But there are ways to secure your network architecture to prevent a majority of threats, whether that's the use of data diodes, which is a one-way data transfer, where maybe the AI or a machine learning model only gets to receive data and it cannot send any data back, right? In this case, you don't have a closed loop control. A data diode uses a light kind of sensor where it kind of does a sort of Morse code on a light across a filter to send data, and it's hardware that doesn't allow any communications back to anything that's receiving that data. That is probably the equivalent of an air gap in a tank, right? creating an air gap in your data source is probably the strongest type of security you can have. But of course, no system's perfect. So even then, you run risks uh, of local threats such as phishing or anything of the sort, which most IT systems and most IT departments should have policies around. But overall, AI is relatively safe because we make the rules. It's not going to do anything outside
Mhm.
of those rules. Data security as a whole, there's ways to protect around and engineer around, as we do when we design our water treatment or wastewater treatment plants. And I hope that's a good explanation of how we can at least manage some of the threats that are present in today's world. Is
Yeah.
there a follow-up to that there?
No,
Or
looks like you got it. I'll pop on if there's another question for you, but I think that was perfect for that one. Thanks.
yeah, no, that's a very good question. Data security is a big thing, and within Autodesk as a whole, working close with those teams to develop the right process to help our customers through that data architecture or that network architecture and advise them in a good manner. It has been quite the process, and we're always here to help and advise on the best ways to go around it. So if there are concerns in regards to that, we'd be happy to take a look at those specific concerns. But yes, water treatment. So this is a very, very small example of kind of your traditional water treatment process flow diagram, right? You have your feed water. Normally you have some sort of censorship or instrumentation up front. There's lab samples that are being collected every single day. Some sort of flock flock being added within that chemical process or within that treatment process. And then, of course, some sort of filtration, tertiary filtration. Sometimes you have a conventional sand filters. Other times you have like a membrane, right? In particular, for this kind of, actually, I'm just going to go ahead and use this. Come over here. So one of our traditional approaches in one of our customers over on the East Coast was to forecast, as I mentioned, and I'm going to reference back that strategy that we use to forecast out water quality, right? We're going to look at data quality, not just those real-time data sensors at 15-minute resolutions, but also the lab data. That's very important because, as many of us may be aware, there is a lot of noise in sensors, or sometimes sensors can't be as reliable as we'd wish them to be. Other times, our staff gets like very stretched thin. I say I haven't worked in a utility in about 2 years, but still, um, staff uh, can be spread thin, and which can maybe cause a sensor to require calibration and just maybe slip through the cracks, and maybe that sensor doesn't become that reliable. So it's very important that in the process of reviewing all this data with that 15-minute resolution, that we're also comparing it against the lab data, right? What we do there and what we allow these machine models to do is we allow them to understand how they're correlated, the margin of error between the two, and also validate each other's data. So if a sensor is going off the rails maybe, and you don't have good sensor health, and someone and lab comes back and adds that lab sample data, or validating that data source, and you can get that alarm or that alert that says, hey, this is off. In the meantime, since this data, this sensor may not be calibrated correctly, what it does, it can inference the right water quality parameter to forecast out what you expected to see within a very specific day, right? Um, if rain is involved, right, it takes weather into consideration, and it uses a numerical approach tied with a statistical approach to forecast out exactly where it is that that the water quality is, or a band of water quality in which is to be expected within the next 24 hours. In this particular uh, plant that I'm kind of showing a little bit of data on, because this is an outcome-based approach and we're taking that OPM-based approach, all this data is being fed into these models and asked to solve and change those control actions to solve for specific key performance indicators. This particular case, it was to reduce operating expenditures and to maintain effluent compliance limits. The critical ones in this one were ammonia, TSS, and COD. What we found is that we were able, well, it's not even we, it's more so the system in itself was able to classify and create different clusters for different operating scenarios, very evident of which are the seasons, right? Every season they were finding their raw water quality was different. And in that regard, it was able to say, okay, based on the time of the year and what we are reading right now, we understand this is what we have, and that and that the facility's been overdosing on large of its coagulants and pH control limits across various sections of the plant, right? In that particular case, it started recommending those control actions to reduce specific dosing, eliminate the need for too much lime addition, and of course, ferric and polymers. Uh, this is just an example of some of the reports that are spit out by Imagine, which is our artificial intelligence that sits within the platform, and some of the savings that were realized in utilizing this outcome-based approach or this OPM approach. So this kind of just goes back into repeating a little bit of what I just mentioned, right? We actively monitor the status of that raw water quality, because that's the most important part of building these machine learning models, is understanding what cluster, what operating scenario we lie in, right? Once the machine understands, hey, this is the operating scenario I've been in the past, and this is the numerical relationships associated with today's approach, we can then track those key metrics, those outcomes, which are normally put on here by a planning engineer or a process engineer, and allow the system to use a machine learning model that's both penalizing for any out of compliance recommendation and giving rewards for all the specific KPIs listed. So this is a reward penalization model where if for every dollar saved, if a KPI or if an outcome or objective is listed as, hey, save me money, and you have a fixed rate, like let's say water loss, don't lose, save me as much money as possible, the system is going to look for that reward, and it's going to get a reward for every dollar that it's saving. And of course, for every time that it needs to fit within the rules to meet compliance limits and spend more money, it's still going to feel penalized, and it's going to look for ways to optimize around by maybe looking for another control action. Maybe that other control action is reducing the amount of recycle or increasing the amount of permeate through a membrane, decreasing the downtime and the associated dollar value of downtime of a large piece of equipment, whether that be a filter, and it starts looking to optimize recycle or CIP cleanings on membranes or recycle rates in an RO system. Very, very useful. I'm going to stop right there. Are there any questions right now, Tim? Or
Yeah, a couple came in. Two came in here. One, how are AI models different from just a kind of a traditional SCADA system, would you say? Kind of what you're describing here with Imagine. How's that different from SCADA?
yeah, so SCADA, the SCADA system is a system of alerts and it's just a display module, right? AI is solving for a problem. And I'm using AI, but really at the end of the day, it's a type of artificial intelligence. That's a machine learning model. SCADA, you analyze, right? Or your operators analyze. You go to your control room, you take a look at what's going on the screens, And then based off what you see, you pick a control action, right? ML does all of that on your behalf, but also solves and iterates various solutions by simulating different processes before recommending an action, right? So it's like maybe it's a similar situation as having an operator say, hey, it looks like we have high turbidity. Let's adjust our dosing over here, right? Let's increase our ferric dosing. They go and increase the ferric dosing and they wait for it and they look at the outcome and they keep adjusting until it gives them the results. The big difference here of using the machine learning models, it goes through those iterations for you on your behalf. It simulates that on your behalf and gives you an answer straight up, right?
Yeah.
And not only is it doing it then, it does it for the next hour, the next 4 hours, and the next 8 hours based on this on the predicted water quality.
Yeah. And branching off of that, we just had a question come in. So that's SCADA, AI, machine learning model. Those are the differences between those. What about, and maybe we'll have to come back, uh, Lalith, with you with a answer if we don't have the understanding here. But what about that compared to an artificial neural network as well? How would that be different? And yeah.
Well, an artificial neural network is a type of AI, right? We, to be very clear, we don't always use that type of AI, right? But it's kind of similar in that regard. And for those that aren't too aware of what the I guess the person that asked the question here is alluding to, it's just a set of multivariate outcomes or solutions. It's an algorithm with multiple unknowns with various disturbance variables, right? So what you end up is with kind of a network or a system that is interrelated with one another. But it's very similar in that we use that kind of system to train our models. But at the end of the day, because what we have on the ground is what we have on the ground, there are pretty direct numerical relationships that will tie us to a very specific operating curve, which I'm going to speak to actually here towards the end of this presentation. Yeah.
Perfect. We'll let you keep going before we hit you with some more questions here.
Yeah. So I have three more here before I kind of tie everything together and how these systems tie together to generate a very good kind of OPM strategy for utility as a whole, right? So I'm going to kind of fly through a couple of these. So in collection, I think many of you guys have heard of how we've used some of our systems over at Glasgow Smart Canals to optimize canal levels based on flood risk and navigability requirements, right? Using ICM Live, which used a whole bunch of SCADA information, and we were able to run multiple simulations and optimize specific controls like that needed to happen. That results in, hey, being able to optimize and enable more storage within the system and 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 generate or at least a justification for more land to be developed, right? It's the same concept here, right? We're using those same concepts that we use in ICM Live, applying some an outcome-based approach as well, where we're just letting a machine say, okay, what else can I do here? Could I operate the system and get more storage out of it? Could we leverage storage in another part of our network to relieve having to maximize the storage at this specific area? Other examples of how we're utilizing the same sort of data inputs, it's predicting SSOs, right? Where they may happen based off its historical data sets of where they have happened, of course, hydraulic analysis and storage requirements, odor control dosing, right? We had a client over here on the West Coast here in SoCal, where I'm located, where they were just looking to figure out how to reduce H2S by 1 milligram, right? That was the outcome. They're like, hey, what do we need to do to reduce H2S by 1 milligram? We've installed all these H2S sensors. We have all these monitoring manholes, and we have all these dosing stations on our main trunk lines. But we tend to set it and forget it and just overdose and spend millions of dollars to just keep H2S at a manageable level. But allowing a system to go through those iterations, here you have your influent quality pretty well characterized by both the hydraulics of the system, which is our ICM solutions, and then our machine learning models utilizing all that H2S data and air quality data to understand the real dissipation and reaction that's happening between some of the chemicals being used and and uh, and the wastewater itself. Uh, Using that understanding, we can create a process curve, which I'll show here in a bit, and track and reduce costs and actually set specific set points to make that goal happen. Reduce 1 milligram per liter of H2S. Then these are the set points that you need to have. This is how often you can change them so that you can reduce your expenses even more, or so that you can avoid these situations where you're just stuck overdosing to prevent any sort of claim or complaints on anything of the sort. This is coming back to that H2S sample that I was saying, where the total spent for a year just in odor control was $4.5 million along several trunk lines in the large metroplex area. And the data was there, everything was there in order to be able to reduce costs. We simulated the costs, we simulated historical models by 1 milligram per liter, and we're in the process of actually implementing and actually putting that stuff out there. But we expect up to 775K. That's $750,000 in savings by allowing a system to simulate, go through those issues. So distribution for some of those that may have missed our last water talks a week or two ago. This is a kind of a brief sample of how that data and these machine learning models were used over at this utility. 7 million residents, 32 district meter areas, kind of equivalent of a pressure zone, but not always. DMA can also doesn't necessarily have to have different pressures. They're just isolated areas, and is distributing 650 megaliters annually. Typo there, I'll have to fix. Again, we follow that process. We monitor all the live data. We validate the data utilizing historical data, and sometimes not just utilizing historical data, but utilizing the hydraulic model itself, right? Sometimes if you don't have those DMAs available or anything like that, you might be stuck in a situation where you have to generate kind of a virtual DMA, right? Or a virtual segment of your model to understand or to give the machine knowledge of where the boundaries end within a specific system. In this particular, with this particular client, same system, same operational scenario. We push out recommendations on what is the optimum level for a storage tank, elevated or ground. What time of the day should the high service pumps be operating to keep those levels steady? And how does this compare to our tariff rate or our rate structure for energy? And we can optimize around using the pumps at the right time of the day and maximizing the amount of storage in the system in order to save money and energy and overall energy use, right? Wastewater treatment, and then I'll stop. So in this particular case, we have a wastewater treatment plant, very similar concept, 17.6 MGD, right? 4 parallel treatment trains, in systems where we have trains, we have an even easier kind of time in validating some of those model results. We can isolate a model or isolate kind of a recommendation to a very specific train and use the training data or use the data like from that process to feed other trains, right? It's the very same way that we can use the data from all the implementations that we have to help these models further understand some of the numerical or biological relationships that are being experienced in different types of processes, right? Treatment conventional activated sludge is a pretty well-known science, right? At least that process. But of course, as our limits get stricter or anything of the sort, a lot of people are starting to kind of look to more advanced or BNR systems, get some enhanced nutrient removal systems, whether that's shifting over to a modified Bar-Denfo or MLE process, all of that just alluding towards, segmenting your reactors such that only portions of your reactors, get oxygen, so you can have some anoxic zones available, to get some biological phosphorus removal or anything of the sort, right? Uh, these systems and these simulations take data to happen. For those that are knowledgeable on BioWin or GPSX or something like that, engineers use these systems all the time to understand, hey, do we have the right amount of capacity, like hydraulic capacity, to treat and to maybe even segment some of these reactors to get very specific type of treatment out of this. And what they're going through is a simulation process. Okay, we're going to grab data and then we're going to simulate all these processes. Now, if we allow machine learning to generate a lot of those simulations for you, we can really like begin to understand what are the real capacities of a system. And because those boundaries are already automatically generated to actual conditions of your past, you can really draw a very good operations curve for overall system efficiency. In this particular case, we had a couple of goals where we wanted to see whether or not the system could solve for either higher quality water or just optimized savings, right? In our operations costs. When we look at a treatment plant, especially in wastewater, there are so many more components associated with that. We have the energy associated with your aerators, you have mixers, you have recycle rates being some of your biggest key components to your reaction, to your biological reaction. Um, just roughly speaking, right, for every Q that you put into a wastewater treatment plant, most of the time in a conventional system, you're recycling, and that means you're pumping back to the head of your plant 4Q, 4 times the amount of water, just to keep a steady biologics, keep that your biologics steady. But in this particular approach, we took two different, we prescribed two different outcomes to see what we could get. We said, okay, model, I want you to simulate and I want you to generate the best effluent, while maintaining a certain level of cost savings. And then on another, and as a side project, we also asked it, okay, well, this is the permit limits. All you got to do is maintain the permit. Give me an operating scenario for that. And as you can see here from over at the bottom, these were kind of the results from there, right? Where we can get higher COD reduction, TSS reduction, and still achieve operational savings, right? Across a system. But we could also maintain and reduce costs even more by working within that margin of what is the safety factor, the design safety factor of a plant. And it was very, very interesting way to approach that problem. And I'm going to stop right there. Anything before I keep moving, Tim?
Yeah, I had a couple of questions come in, and I think they actually kind of relate to a question that was asked later. Basically, everybody had a question asked, like, what happens if a sensor is unhealthy? How does that affect the entire
Yeah.
machine learning model? It's similar to that. What happens if you introduce a new treatment process into that model? How does that kind of mess up everything that's been learned
Yeah.
up to that point? But I think that's kind of summarized in how you can kind of correct for or adjust for those changes to your treatment by this question that asks how long is the model training kind of period. Right, so maybe start with that one. If you start with how long is the model training period, I think that kind of helps to answer those other questions about different disturbances that might happen
Yeah.
there.
Yeah, of course. So at least with us, every company is going to be a little bit different, but at least with us, we do go through an implementation period whenever we I guess hand off or we sell Imagine, right? That implementation period can range anywhere from 60 days to maybe 120 days, depending on how many models are built within that, right? But what comes out of that is a pretty detailed exploration report and data correlation analysis and a trained model, ready to use trained model that's already solving around a desired outcome, right? So that's usually around how long it takes to train those models and get everything set up. It could take a while because sometimes a person says, hey, I want to solve for X, and it turns out that they don't have the data to solve for X, in which case we got to work with our clients to make sure everything gets instrumented correctly and that we collect enough data to be able to train to. Once that model is delivered, though, it continues to go. It continues to move. It's adaptive. So as it reads more information and as things change in the plant, those conditions, the model adapts and moves along that operating curve um, to adapt. And I keep mentioning this operating curve, but I'm gonna. It's a good way that I summarize all these things as they come together. But it self-adapts, right? So if you change a process somewhere halfway through, so long as it's not something like we just added 80 MGD to the plant, right? That's a huge CIP project. Most things like, let's say, changing a piece of equipment or maybe even um, segmenting your reactors, adding another zone, those things get adapted to, and the model reads in the data and regenerates new system curves, which then it uses to do so. So most things when it comes to like updating a plant or a system can be accounted for, and if not, usually what that entails is having your process engineer or whoever is normally in charge of doing those kind of projects go utilizing the system to adjust the system goals or the system parameters. Maybe you get a bigger tank, right? And the model is built around a very specific volume capacity. When you get a bigger tank, all you got to do is go in there, change the capacity, and it incorporates that change. Uh, and the results of the model incorporate that change as those improvement projects move forward. I think I covered most of those there.
I think so. Yeah. Going back to the sensor, if a sensor is indicated as unhealthy, if you've got an unhealthy sensor, the machine learning imagine is going to catch that, and it's obviously going to learn to kind of disregard that from the conclusions that it kind of recommends, right, in terms of dosing, in terms of energy usage, kind of thing. And I think
Yeah,
that's a real benefit to the software, to any kind of platform that's organizing and collecting lots of sensor information. And then I've talked to utilities that
yeah,
basically say we've spent all this money on our SCADA system, on hardware, on sensors, and we don't actually know if it's working. I know we've gone into
or if it's right.
utilities or if it's right, and this
Yeah,
helps utilities know what data is important to make the right decisions, right?
yeah,
If you can kind of weed out what ones weren't important, it helps you place future sensors. It helps you make sure that those sensors that actually are important are operational and running and reporting as they should be. I think that's another thing. Definitely is important.
yeah. It's yeah, that's the important part. But yeah, the model is constantly validating those sensors And I would even say Info 360 right now is probably the best to monitor sensor health as a whole, right? There are specific rules that you can set so that as it validates the data, because we're not just looking at SCADA, we're also looking at like Hawk Winds or whatever database you may be using to collate your lab data. All of that is being aggregated, right, and put next to each other. If it sits outside of a specific band of whatever the lab is coming at, it's either going to say, hey, your lab is wrong or your sensor is wrong. More often than not, your sensor is wrong, and it's going to alert you. And then to spit out the right recommendation, it's going to use the right data, or it's going to interpolate based on, it's going to inference that data point in order to give you the right kind of thing. Because we don't want to feed the model garbage, because garbage in, garbage out. So validation, data validation is a huge part of giving the right recommendations into these models. So a little bit out of order probably, it's probably good for the end of the presentation, but I've got a couple more things to share. But really what's missing in a lot of organizations when we start to implementing these things, it's the trust in some of the technology, right? And that's on us, right? It's our responsibility over here at Innovyze, Autodesk, and a whole bunch of other technology providers to justify and be able to provide the right reports and understanding of how the technology works. We need to rely on this digital twin. We need to know who, what, when, where, and why, right? We need to do all of these things. And if we're speaking to engineers, we can't necessarily show what's going on under the hood. And it's really difficult to just be like, okay, the model tells me I should do this, but I've been doing this for 10 years. I think differently, right? So that trust is a big part, and we'd love to continue to get some more feedback on what kind of information can be provided or what kind of more education sessions can be brought, maybe on model trainings. I think it'll be very, very useful. So OPM on the overall for the utility. So using that OPM strategy for utility. I just spoke about these different four components of how the technology is being utilized inside. And what you see inside all of these all of these segments here are those four different components. And within those four components, there are even more components. For the sake of visualization, I've tried to simplify this to those four components, because if we have more than four corollaries into a model, then yeah, we start to lose the fidelity of a model, right? That's where using some numerical approaches and or some of our engines and models from our core product lines becomes very, very useful and helpful so that we can determine or draw the lines and boundaries of our system. In an overall utility, at a management level, you may just be curious about like, okay, can I justify my rate increase, for operating my utility and, my future, right? My future demands. That all fits into distribution, how many meters are being used, and how much money it takes to treat it upstream and downstream, and all feeds one big model, right? These are all models inside one big model that can be used to generate an overall outcome, like our mission for utility. Like our mission is to go green, right? And go carbon neutral or energy neutral at our wastewater treatment plant, right? You can set that outcome on a model and ask it to solve for increased methane production, right? At a digester facility. From there, spit out CIP reports on, capital improvement programs to understand when specific equipment needs to be added to increase the capacity of energy production, and solve those big utility missions at a high level, and understand what steps are needed in the process to get there, right? This is why we gone towards the cloud approach, right? The cloud approach allows us to put all these models, which is sometimes hundreds of models within that overall model, in one single place in our platform. Um, and the platform allows us to use that outcome-driven approach and make thousands of iterations, sometimes in 15 minutes, which is a lot of time. Sometimes it's a lot less than that, but I like to use 15 minutes if you're going to ask it to analyze all 4 levels of your water. Uh, but it's not the hours that most of the time it takes to, like, let's say, run a simulation for a hydraulic model or anything of the sort. It's a it's a very good way to use the technology of and the computational power of the cloud, which is probably the most important part of you utilizing the cloud. Not everybody has fancy computers, but we can definitely share those resources out on the cloud. Um, One good example that I like to use on where the machine learning technology is going and how it's being used as well, or at least here within Innovyze, is to think of like our Info 360 as your operating system on your phone, whether you're on iPhone or Android. Our product lines will become apps within that, right? Imagine being the equivalent of your Siri or your Google or Hey Google, right? You can ask Imagine, hey, how do I make this happen? Or what is going on? And it can depict that area for you as opposed to having to analyze multiple data streams at one time. Um, so this is the famous operating curve that I'm talking about, which I think it's a pretty good depiction of how our system works, right? Or how the machine learning is working. For various operational scenarios, or what we call clusters, right? Different operational curves are built. And what you see up here at the top is kind of like an S curve at the top of close to this flat line. Somewhere in the middle of that S curve, if the system's designed right, is what you'll have is your design point. That's where your system's operating, that's where it's going. When you ask the model to do specific things, what it does is slides up and down your operating curve as you would a pump curve, right? If it operates kind of lower down here, you can lower your operating costs, but of course, you got to stay within a limit. Maybe that permit limit being 90% removal across the system or 90% efficiency of a very specific process. If you're trying to achieve higher water quality, then it moves along that curve higher up. There's a curve generated for your specific system for every operating scenario available, right? That's what the machine learning, that's what the labeler is doing. That's what Marie Kondo is doing. She's constantly labeling, okay, this is the operating curve for this scenario. This is the operating curve for this scenario. And the system pulls that operating curve for a very specific scenario. Maybe it's a demand model for a very specific time of year, specific time of day. And it says, okay, this is the operating curve. Now slide up and down the operating curve to solve for a very specific outcome. Output the inputs required to make that happen. This helps us, ensure compliance, optimize around water quality or cost performance, or even just maintain that design point, which can sometimes be the most optimal point. But to maintain that, we have to adjust it for every single operating scenario. Questions, Tim? I know we're running short on time, but I think we've captured a good amount of questions. I had a sample here of where we're using it on a dewatering, right? Where we, in the same way that we would use Siri, so like Imagine optimized our waste treatment cost per dry ton in our dewatering facility. And from that, you get different outputs for how to run specific facilities. In this particular case, the steam generated in this area was actually also used to go generate power. So which was a component of the cost associated with the dry ton. But in this particular case, we got different outputs on how to operate, reducing our overall costs.
Yeah, no, a couple things, different questions have come in, a couple comments before. I've put in the chat a link to learn more about Innovi's specific artificial intelligence machine learning solutions, namely Imagine. You can find quite a bit of information and resources on our website that go into more detail than Javi's going into now. Of course, the session is being recorded, so you will have access to the recording afterwards. Um, Other questions that have come in. Um, you going back to that operating curve. I think you covered this, but just to be sure, it was right there. Jishnu asked, what are typical predictors for predicting the operating curve? Could you give some examples? Um, yeah, I think you might have covered that, but I just wanted to be sure, I guess.
Typical predictors for predicting the operating curve.
Yeah, typical
My
sensors or data
understanding,
sources, I guess. Yeah.
yeah, my understanding is what do we look at in order to generate that operating curve? It's all dependent on that system being modeled, right? If we're in a distribution system, we have that process knowledge to understand, okay, to generate a demand profile, we know that there's demand profiles associated with season, time of day, weather, sometimes events, um, and we overlay. So all of those things are used to create demand profiles, right? But then on another area, because these are multi-dimensional operating curves, we also look at historical data or CMMS data or anything of the sort to understand, okay, maybe a pump is not running, or maybe a specific area of town is known for having issues because of the age of the system in that area. So we look at that asset data, and based off that, we can get risk scores and apply risk factors to the analyses to determine, okay, maybe it's best to deliver water in this way through this manner. So the factors are very specific to the problem being solved, but nevertheless, they're just inputs into the same model. The validation process, again, is the most important, because if we can't replicate that analysis or have a good labeled explanation to why there might be an outlier in a data source, then it's just that it's an outlier that would result in bad model outputs. So we need to remove those if they don't pass the validation criteria.
Perfect. Perfect. Yeah, I think I'm not going to get to quite all the questions here today. Thank you all for the questions. I think these have been really great, and hopefully we've
Yeah.
gotten satisfactory answers. If not, if we haven't gotten to your question today, we'll be sure to get to it in a follow-up email here. You'll be hearing from us, but I think this is a good kind of summary question maybe for us to wrap up on here with a couple minutes remaining. Javi, what's the next step to have, again, this buzzword is used all the time, digital twin, to have a digital twin? What's the next step for doing that? This concept is often subject to interpretation. Is this it? Is this the digital twin, or is this just part of it? Is this the next step? What do you think on that?
This is part of it. Using a machine learning or the OPM, the operational performance management approach, that strategy, I say it's a perfect first step, because you pose a problem, right? Or how do I do this? Or a question, you ask a question. And only by asking that question to the model can you understand where your gaps are, right? The digital twin is the actual digital representation of your system, which you may have in some regard, right? If you use one of our core products, you already have a digital twin. Now, is it up to date? We don't know. We don't know until we know. But applying those machine learning models and analysis lets you know what you're missing, right? What are you missing before you can start asking more complex questions, right? And some of those questions are, hey, can we get an equipment control schedule for our entire system for the next 24 hours, right? Predictive maintenance schedules, maybe quantify potential non-revenue water based on, ILI, which is what our Info360 product does, right? Uh, Analyze system capacity, levels of service, which is very important, especially in wastewater. before we get to that stage, we need to collect the data and understand what is missing, right? The more granular that data set, the higher the resolution. By that I mean, if you have an actual live sensor data sensor that's out there collecting every 15, 30 minutes, the better your results. If you have lab data or you have maybe a CIP program that gets generated in tables by consultants or anything like that, that is data too. Now, the resolution of that data may be 1 year, 5 years, or anything of that sort, but that's data too that can be used in these models. With, of course, the granularity of that data really giving you determining the outcome and the efficiency that you get from the data. I would say first step is to do some sort of database analysis, right? Understand where your organization is storing your data, right? If it's in 1,000 different places, how do you get it into one place, right?
Mm,
Innovyze offers Info360 as that solution to start getting all that stuff into one place. That's step one. Step two is understanding what data is missing in order to achieve very specific goals. We also offer those kinds of services that provide guidance on how to get to these stages. Yeah.
mhm. Perfect. Again, thanks for all the questions. I've answered some in the chat just via text that most folks, y'all should be able to see. One key thing is we've mixed around a lot of different product names. I think it's good to understand Info360 is a platform. There are lots of different tools and modules that can
Yeah.
go into it. And Imagine specifically is focused on the machine learning and AI. It's a component of Info360. So there are a lot of infos and
Mm-hmm.
different product names here at Innovyze. We know it's confusing, but Info360 product, Imagine machine learning AI specific component of Info360,
Yeah.
and Info360 can do a lot of things and will be doing more things in the future as we continue to build it out. But with that, I think that's looking good for questions. Again, if we didn't get to your question, we'll be following up. We're 2 minutes after here. Thank you very much, Javi.
Of
Yeah,
course.
and
It was a
appreciate everyone
blast.
for
I love
joining
talking
us.
about these things.
Yeah, very good.
Yeah.
Thanks, everybody, and we'll talk to you next week.